as we all have seen, the huge advances in machine learning have so much promises. And as I have been following probably development of hundreds of algorithms already, and I haven't really seen any one of those failing. Most of them are successful. But for some reason, we haven't got them yet in clinical use, and that's a pity. So I get really envious when I see that from other fields like ophthalmology, we have already FDA approved algorithms using deep learning, and also from the radiology side. So why is not pathology there yet? And yeah, we need to bring pathology to this level. So yeah, this is a disclaimer. I'm a founder and co-owner and chief scientific officer at Iforia, former FIMIC. So, but most of what I talk today is related from the academia. So the outline of these challenges that I put up are mainly related to development. I don't go into this like deployment, implementation, and commercialization, and so on. So mainly quite practical, on a practical level. So I could probably start by the samples and the data, because as we have also been discussing already today, that data is king. So you need the data. But we have limited access to data still. So although you collect quite good series from the research project, you still end up with maybe hundreds or maybe a few thousand of samples. And that's regularly not enough for really validating a new system. So, and especially of course the clinical data we need. So we need to share data better. We need to form more joint projects and these so-called data lakes and on a global scale, because otherwise it will not succeed. So, and we of course also need the annotated images. So we need annotations. Those are crucial for this. There are different types of annotations, and I will mention a few that maybe would be less cumbersome to collect. So, but we need to create public libraries and repositories of annotated images. So we need to do more to share. Although you would have a great series of samples, maybe in thousands, then when you sum up everything and you look at the clinical data and the outcomes that you have, then suddenly you have incomplete data, so you lose a lot of them. So you might still end up with just a few hundreds of the thousands that you started with. So we should strive for completeness of data, go back to the clinic and get those data that are missing. Revisit the hospital records, revisit the pathology archives to make it more complete. And we have, of course, then when we have collected the data, we have it available, we see that it's most of the time full of artifacts and difficult things to handle. So you will lose also there. So we need to perform quality control, and we need to, in case we have a poor sample, we need to recut. If it's a poor stain, we need to restain, and we need to make the data complete to be able to make this progress. So we can't, of course, get rid of all the variability. This is just from a breast cancer TMA, and we immediately see the huge variability, both in staining and sample quality, and although this is like in a small scale, but this is reality. So we need to just live with this. So then regarding digitization, what I see as largely still missing in digital pathology is the third dimension. We need a third dimension. We need a Z level. I mean, we cannot compare to a regular microscope if we cannot see in depth also to focus and to look through layers of the focal planes. So for some reason we haven't got this yet. So to all the scanner manufacturers, yeah, you need to do a better job here. We need a Z level. So develop that, and especially also develop the third dimension compression. We don't have, as I know, reasonable ways of compressing the third dimension, the Z level. It should be quite obvious that you should be able to compress a lot, because now when we scan in many planes, we end up with like terabytes of, some images we have are even 10 terabytes, just one single sample, because it has the Z levels. So we need to have that. And maybe we need to store some data temporarily. We have all the poor focus, we have incomplete areas. So again, quality check algorithms are needed to find these poor focus areas and then just rescan. And we have the color and staining variability, as I showed you in the previous slide. There are methods to handle those for standardizing the staining, to normalize the staining and calibrate the colors. And what is also important, we have the various scanners available and scanner updates. So if we switch the camera in the scanner, you have a kind of a new instrument there. It's not the same. So we need to, when we report on what we have used for scanning, we should always report what is the current version of the scanner, what the properties are of the camera, because otherwise we will not be able to compare. So here is, for example, two TMA spot, or one single TMA spot scanned with two different versions of the same scanner. So just the camera has switched. So I don't know if you see, but there are quite clear differences. So then the annotations. So we have variable quality of annotations and segmentation. So here we need to be careful and patient and check for mistakes. So this is really crucial, because the algorithms are just as good as the teacher. So here is a short video showing an annotation of CD8 positive cells. So this is a good annotation. It clearly follows the margins of the nucleus. But then here beside you have totally different level of detail. So it's not exact at all. So those will of course be replicated. The neural networks learn these patterns really easy. So they start to give you also those poorly poor margins of the results. So, and this is the difficulty. It's really hard to find annotators who have the patience to do this in a way that it follows all the details and it keeps a good quality. It's really hard to find those. So, and also, if we do annotations, we tend to end up with only examples of the easy classifications. So all the ambiguous cases, then those you leave out. You don't annotate because you cannot decide. So there we need to really make hard decisions, because what you annotate is what you get. That's the reality, especially in the deep learning context. And we have a lack of annotating pathologists, so lack of experts who do this. I don't know how we could better motivate. We probably have to give more resources, more time, better interfaces, maybe also to a certain extent crowdsource the annotations. Although, as in my experience, the best results we have achieved is regularly that this one annotator is doing one project first, and then you can verify using other data. And the number of annotations. So regularly, almost in all studies that I have seen, more is always better. So, and especially you need to cover the whole spectrum of possible morphologies for a certain target. You cannot leave out, and that was especially true, like say in the testicular cancer project that we did together with Claire, that we have a kind of consistent target, the immune cell, but it exists in very variable, against a very variable background. So you need to have all the spectrum, and you need to have it's not only like we don't only need the artificial intelligence, we need an intelligent annotator. And we can use tricks to improve. We can use controls negative controls also from other domains to improve the classification and segmentation. So this was the one that Claire showed, where we annotated immune cells in H&E stained tissue and then trained a classifier to identify the immune cells in the tissue. So, and we reached a decent agreement with the human observer. So 0.88 in this case was pretty good. We were quite pleased. In this particular test, we used about 1,000 annotations of immune cells. So then I was curious about what happens. So this was some result from the 1,000 annotation. So you see that in certain clusters where there's a lot of immune cells, it leaves quite a few of them undetected. So the F-score here was 75. Then if I increase it to 1,500, then we chose really difficult ones, those ambiguous ones, and put them, added them to the data set. And actually, suddenly this made the validation set performance worse, because we had added those difficult ones. So it's really a lot about how you choose and how you select. So then we just continued, and we added, so we had 4,000 annotations, and then you start to see that it comes closer and closer. So now the F-score is already 87, and then we continued even from this up to 8,000. I think then we started to get really good performance. So it's a lot about just adding and adding more data. So then the algorithms. So then the question is, like I showed you, the immune cell detector. When is it good enough? When is it good enough? Because we have an uncertain target. We have annotations performed by a human observer who also makes mistakes. So when is it good enough? I don't have an answer to this. We have then the multiple platforms, so and multiple network architecture. So which one should we choose for a certain purpose? That's impossible to say without these competitions or shared and standardized reference samples. Anyone can claim I can create a hugely accurate algorithm by choosing those easy targets to my training set. So actually, without this shared data, the accuracy results reported in articles just doesn't make sense at all. And then the question is also for our domain. Now most of the published results, they use transfer learning, meaning that the actual network has been trained on cats and dogs and bikes and so on. So what happens if we really would have a lot of data from our domain and would train end to end? I don't know how much improvement we will get from that, but probably quite a lot. But for that we need, again, big enough data sets from the domain of histology and pathology. And then one of the biggest questions is, do these algorithms really generalize? So there is a lot of uncertainty with regard to that. And how can we establish robust algorithms that are not too sensitive to artifacts? And how can we really make them reliable? There are examples where you have created synthetic data that actually can be faking a tumor in a sample. Of course, those kind of extreme cases should also somehow be possible to tackle. And should we initiate, like in the Human Genome Project, should we initiate like a Human Phenome Project to really make this possible? Because there is I don't see any real reason why we couldn't automate the entire pathology, field of pathology. So the generalizability of the deep learning algorithms, I want to just show you one example. This was an algorithm trained for detecting CD8 positive cells. So that was trained using examples, annotated examples of cells, so it performs at a high accuracy in this CD8 staining. So then we took another staining, CD3 staining, and applied this same CD8 algorithm. So the chromogen is the same, it's the DAB chromogen. So, and it works really well also in that. But this was actually from the same lab and using the same scanner. But still, this is quite convincing that it is possible to transfer. And here is even another staining, a Langerhans staining, and the CD8 algorithm was applied to this Langerhans staining, and it also works. So to some extent, you can probably start to find this that generalize well. And then we have the computational challenges. These images are still posing problems because we have these huge images, and especially if we start doing Z-level scanning also, we have even bigger files. So this is still a problem, and we need to have better compression and storage for this particular purpose of digital pathology, because still we want to have the data. We cannot do anything without the real data, and with all the levels of depth also included. And we need, of course, high performance computing to run this and train, especially train the algorithms. So the graphical processing units, sometimes it's good to use cloud solutions. Sometimes you also can use local server farms to especially to train these classifiers. And then how do we connect these scanners to the computational infrastructure? We really need also faster networks and better bandwidth. That's to me a bottleneck now, because you would like to transfer directly from the scanning immediately and then get really fast processing of the images. And then to end, there are some other challenges, of course, many, but one is like ownership and access to images. We don't want to have certain companies only having the only access to images and not giving this for others to also evaluate and develop on. And what if AI goes wrong? So always you will need for a long time pathologists, clinicians who are responsible and make the final verification of the results. And then what to do with rapidly improving and updated algorithms. You would need to allow it to be a moving target, and you have probably seen the FDA's discussion published now on this. So this document, if you haven't seen it, it's really interesting, and FDA has clearly seen the need for having a process for allowing these algorithms to improve over time, which is of course necessary. You cannot have fixed algorithms in the world of deep learning. You need to allow them to improve. So, and then the one question is how to handle tens or hundreds of AIs for the same purpose. That we will also see, of course. We will have many solutions for the same purpose. And how can we then? We need to maybe then have even some consensus algorithms. So these are just some examples of the consensus you need to achieve. This is like, again, from the immune cell detection. We could agree that this is likely to be an immune cell. What about this one? I don't know. We need to agree. We need to have good ground truth. Same here in scoring of immune cells, of stainings. So this is probably positive for DAB. This is likely to be negative, maybe. So again, examples of this. And we don't want to have the situation where the AI is just another subjective expert. So this is likely to happen, I think, if we cannot agree upon other methods to evaluate and to assess and validate. So this is an example from Gleason grading, that here we have just the model is just another of the experts and disagreeing with two of the pathologists. So I think the solution, one solution to this would be to rather than to try to replicate an expert, just look for the real endpoint you want to achieve. If the endpoint is to predict outcome for the patient or predict response to treatment, why should you do some intermediate, why should you try to replicate an uncertain classifier like Leeson? You should try to instead train directly towards the real endpoint, the outcome that you want to achieve, the patient survival, for example. So here is from one of our studies where we used cancer TMAs to predict. We had a pathologist, actually 3 pathologists predicting the outcome of colorectal cancer and breast cancer, and then we did the same with the direct training of against outcome. And we saw that we can achieve a higher discrimination according to outcome using the deep learning network than the trained pathologists. And then, of course, this is the interesting question, that can we then go further and discover novel prognostic factors? So this was published last year based on colorectal cancer. So the only input was these small TMA spots, and then we showed that the AI had significantly better discrimination compared to 3 experienced pathologists. And then we want, of course, to look at what is the network seeing, and this is now a work in progress. So then, as a conclusion, I probably will leave you with more questions than answers, and I think that we agree that the quality and the selection of, and the annotation of training data in AI is crucial, and we need to organize so we can have better access to data. And how could we get more reliable ground truth? And how could we, maybe we should really strive for a global data lake that could be accessible, not only national, but global. And there is a clear risk that we will end up with even hundreds of AIs for the same purpose, and with unclear accuracy. So we need to have this shared data, otherwise we will not be able to say which one to use, which is the best one. And ground truth given by a human observer will always be subjective. So we cannot we cannot pass that. And maybe we should then go rather for direct outcome supervised learning than feature supervised learning. So I thank you for your attention, and this is our group in Helsinki. We are partly from the medical domain, partly from the technical, working together. We have also now a grand challenge at the University of Helsinki related to this digital diagnostics, where we have a network of clinicians and pathologists working together with the computer scientists to try to address these issues. So thanks for your attention. I'm happy to take questions.
I can see a few hands.
Johan, very good assessment and of the field, and very nice observations. I want to revisit the question you raised in your presentation. When is the algorithm good enough? When is the human good enough? So at some point they decided that you were good enough to do these kind of things. So do you, in your opinion, do you think that algorithms need to have a higher threshold than humans, or should we establish some standards and say, okay, these algorithms pass the tests that we design for humans, so it is good enough? What are your thoughts?
Yeah, I think that we would think, if you take the outcome predictors, we can clearly measure the accuracy against a little bit more objective ground truth. So when we see that the best performing pathologist, although pathologists are not really doing risk assessment in the way that we did, but still we had this setup. So if the AI performs as well as the best performing pathologist, I would probably be willing to accept it as a acceptable algorithm. Although, of course, we would like to achieve like superhuman performance, and in that domain of outcome supervised learning, we could really measure superhuman performance, because Gleason grading, how could you do superhuman Gleason grading? I don't know. It's probably not possible. But with regard to the endpoints, the more objective endpoints, we can measure that.
Yeah, thanks, Johan. I just want to echo what Metin said. Really, really nice presentation. So I want to be a little more contrarian. So you talked about annotations and the fidelity of the annotations driving the deep learning examples. And then you showed very nicely how after throwing in a lot more cases, a lot more annotations, that the performance improved. I think everybody has felt the pain, at least everybody, all the computational scientists in the room have felt the pain of getting a sufficient number of well-annotated cases, right? We all have, for a variety of different examples. The issue of, and it's not so much that the experts aren't good, it's just, I've used the term butt time before, right? There's not enough butt time to sit and annotate these things. Does that then beg the question that maybe we shouldn't really be thinking about necessarily deep learning algorithms, and maybe we should actually be thinking of algorithms that don't have such a high bar of so many annotated cases? And maybe is it so much the annotations, or is it just us really thinking back to basics, thinking back to fundamentals, and thinking of better algorithms that could get away with a fewer number of well-annotated examples? So, any thoughts?
Yeah, I think that especially what we are looking into now is ability to use like more active learning, meaning that you start with a smaller set of examples, and then you see the results, and then you are able to improve like successively. So then you might, you should not do hundreds and hundreds of annotations if the network has already learned that pattern. It doesn't make sense. So you would like to minimize the number, but you would like to see the results, and you would like to be able to quickly evaluate, has it learned a certain pattern or not? So I think that kind of approach could be really valuable.
Okay, one more question, and then we need to.
I just have a question. I've noted that in establishing the ground truth, the H&E stain seems to be the standard stain. But actually in practice, pathologists don't use only the H&E stain. We often use PAS stain, we use Giemsa, for example. It's typical in hematopathology. And so I'm wondering whether you're limiting yourself by establishing the ground truth using the H&E only. Yeah,
I agree that many examples are from the H&E because that's still the most common type of staining. But definitely we also use, to a larger extent now, also like guidance by immunohistochemistry. So we can combine the modalities. We can even stain with H&E, then wash away, like stain the H&E, scan, wash away the H&E, and stain with other type of stain, and then digitize again. And then you can align these images. That, I think, is really a powerful solution. So it doesn't really matter what kind of stain for the deep learning. Of course, it can be any stain that you use.
I just think, for example, a Giemsa stain, you can differentiate a lymphocyte from a basophil from a mast cell a lot easier than in an H&E.
So then you would like to maybe transfer that information to the other type of stain that you kind of, there are examples of creating an H&E stain from an unstained sample. So you can, with the deep learning, you can go between the different staining domains.